good.
That's great. So I'm starting now. Today I'm talking about this topic, incorporating ground cracks in the estimation of post-seismic landslide susceptibility. My presentation is more really like case study, so a bit different from maybe little different from others' presentation. Anyway, this is the example of seismic cracks, which was seen after the 2016 Kumamoto earthquake. Actually, this location is not involved in my study area, but I think it was really good to show this as an example of seismic cracks. So this is interaction. Intense earthquake can trigger numerous landslides, as you know, and following an earthquake, an area will remain prone to landslides because the ground is affected by strong tremors, so it's really weak. Therefore, people usually care about co-seismic slides, but we think we should care about the susceptibility of post-seismic slides as well. So this is an example. So this is just after the earthquake. Then this is 4 months later. So it's really good to see, good to test or good to check seismic cracks, because we thought it's relating to the susceptibility of post-seismic slides. Because people think susceptibility to post-seismic slides is considered to formation of seismic cracks. So distribution of seismic cracks is urgently mapped immediately after a major earthquake like this. This is an example. This is a crack distribution map identified by GSI, Geospatial Information Authority of Japan, after the Kumamoto earthquake. Several organizations actually made similar maps after the earthquake by reading topographic maps created by LiDAR and air photographs. But as you can also guess, all are different between each other. So proposing a reliable index that can digitally represent the distribution of seismic cracks should help to quickly and objectively locate slopes susceptible to further landslides in emergency after a major earthquake. This is also an example of seismic cracks too. So this study is going to propose a new index, DCI, dense crack index, which represents the spatial density of seismic cracks. Then we are going to examine the association of the index with post-seismic landslide occurrence using weight of evidence and random forest methods. Then also we're going to examine whether the inclusion of the index improves the performance of the model for evaluating the susceptibility. In this case, we use WE and random forest and logistic regression. So this is an example of slide here. And this photograph was actually taken just after the earthquake. So this is a study area. It's located on the flank of Aso caldera. This is active volcano here. And I took photograph, I think probably from this point to this direction. So actually this part is here. It's covered with pyroxene andesite lava, classic volcanic rocks with lots of joints, and covered with aged Cryptomeria japonica. This is needle type tree. The Kumamoto earthquake struck the area in April 2016. Epicenter is more than 20 kilometers away, and this is seismic fault going through the study site. And the maximum PGA recorded in the area was 1,270 centimeters per square seconds. So we identified 196 post-seismic slides, this area, this blue bits, 196 in total. And they are mostly caused by rainfall from June 19th to 29th. So this amount looks really heavy, but this area is really wet with annual rainfall averaging over 2,700 millimeters. And then few landslides were observed after the event. So probably this event vacated also most of unstable soil mass. Mostly they are shallow translational type. And they tended to appear on slopes 40 to 50 degrees, very steep, and along inclines, and horizontally concave, and importantly, with clusters of seismic cracks. They were reported by them in 2019. And since this study investigates the effect of seismic cracks on post-seismic slides, so we targeted only this area where landslides were initiated. So this is calculation of DCI. So this is 2013 January LiDAR data, and 2016 April. This is taken just after the earthquake. So as you can see, earthquake created lots of cracks like this, and simply the surface got rougher. So I used change in surface roughness with a very simple roughness factor, the standard deviation of the slope angle, and just obtained for post data and pre data and calculated its change. And then after that, selected the value over 2 degrees. We just 2 degrees was really good after some examination. Then converts the cells into points to calculate the point density using a kernel density. So this becomes DCI. In this case, we used the bandwidth of 10 meters after some examination. So this is example. So actually this landslide is this. So you can see the scale of this event. I think buildings are around here somewhere, so it's really big. And these black lines are seismic cracks identified. Then these red dots are a change was over 2 degrees, so mostly agreeable. Then we calculated DCI, and this part, we went to field and found it was like this. So after proposing DCI, we inserted into statistical models. The procedure is like this. So just selected cells from post-seismic landslides and also area remain, and divided testing and training, and the same number here. Then used WOE and logistic regression and random forest to make landslide susceptibility model, then tested and evaluated. And 10 data sets were created. These are conditioning factors we use: topographic, of course, with DCI, and also seismic, meteorological. We didn't care about geology and vegetation because we thought this is regarded as the same over the area. Then seismic and meteorological factors, PGA and the total rainfall, they were estimated from nearby stations. So the spatial resolution is quite different from topographic factors. This is based on 1 meter, but here its resolution is like 100 meter. Models are built with factors with and without DCI, and their accuracy is compared using AUC. So this is association of conditioning factors with post-seismic slide occurrence. And this is from WOA, because we wanted to see this contrast value for each factor classes for every 10 data sets. And if contrast becomes positive, which means association with post-seismic landslides is very positive, and vice versa. And here, as you can see, closer to fault, so more landslides tend to occur. Also, stronger PGA creates more landslides. Also, it doesn't apply to the strongest area because this area contains lots of gentle slopes of under 25 degrees with very negative contrasts. And about topographic characteristic, they agreed with a report by SCCTD 2019 I introduced before. Then here, DCI, this suggests the formation of seismic cracks is closely related to subsequent landslides, because as you can see, more cracks means higher contrasts, and sparse formation of cracks show negative correlation. So somehow we divided here with the value of 0.2. Then just checked influence of seismic cracks on contrast or factor classes. So here, just indicate more cracks in a class means more susceptible to post-seismic slides. So that means here strong PGA and also features likely to appear near ridge lines. This is red square. There lots of open cracks are formed and show high contrast or more higher susceptibility of post-seismic landslides. And then this is importance values of factors by random forest. As you can see, DCI is the most influence factor followed by slope angle and PGA. This is consistent with the contrasts. And rainfall and distance to fault were ranked as less important than those factors, even though the positive and the negative contrasts were as large as probably due to the lower involvement in actual seismic crack formation. So this is an example of landslide susceptibility map, and a warmer color means a higher susceptibility. Closer look. So the model with DCI can detect post-seismic slides like this. Without DCI, couldn't do. But WA and LR were a bit oversensitive to cracks. So far, good. However, checking AUC values, all the AUC values indicated excellent or outstanding performance of the models. However, the improvement of the performance was marginal or even negligible. Probably this was because a combination of other factors enabling to express locations where strong seismic wave was locally hit could compensate for the absence of the index. Also, this is the biggest issue. The next, the contribution of DCI could be evaluated higher with better accuracy of LiDAR data used in the analysis. So issue of DEM error. The reliability of the DCI value depends on the accuracy of the DEMs used for the calculation. And really a quarter of the post-seismic landslides were located on slopes with sparse ground points in the 2013 LiDAR survey, like this. So DCI cannot be calculated properly. This limited the feasibility of properly assessing the relationship between them. Also, because landslides tend to occur on steep slopes with densely vegetated, so this kind of issue tend to occur even in 2016 images. And in that case, the presence of landslides was difficult to be confirmed, even though the models suggested it. So I know I'm over 15 minutes now. So just a quick summary and the conclusion. This study proposed a new index, DCI, and it was the most important factor determining the occurrence of post-seismic slides. However, the performance of the models with the index was only slightly improved. So it's probably due to errors in the LiDAR survey data. So probably the contribution was underestimated in this case. In addition, the combination of features where open cracks were likely to occur could also compensate for the absence of the DCI index in the models. But this compensation was probably possible because the lithology consisted of mainly of classic volcanic rocks with joints, because it didn't allow water to stay in the ground. Contribution of the index would be different in the area with subsurface layers of low permeability like volcanic ash underneath. Because in that case, probably cracks would be involved in landslide processes more actively, like deep-seated landslides. So after all, in this study, the high potential of the DCI for evaluating post-seismic slides were presented, but there is still lots of room for further research and development before the index can be practically applied. Thanks for listening.